So in representation theory, one of the big challenges is constructing irreducible representations of a group. Now we know that we can find them inside the regular representation, but unless you can find some way of computing the character table, you won't be able to construct them explicitly. If you just have one group though, the problem can be solved numerically or algebraically. So the interesting cases are when you have groups in families. So the first really nice family of groups to be resolved is the symmetric groups. This was done by Schur and Young, and this remains one of the most beautiful and spectacular achievements of representation theory, even though it's very, very old. So we'll move towards that, but the approach I'll give you will be combinatorial. It will not follow the lines of Schur or Young. We will first construct representations of the symmetric group using sets on which the symmetric group acts. So if you have a group acting on a set, you can look at functions on that set. They form a vector space and you get a representation of the group on that vector space. You've already seen an example of this. The regular representation is precisely this. You look at the functions on the group acts on the group itself by translation, and so more generally these are called permutation representations. So the setup is that you have this group G and it acts on a set X. So this notation just means that G acts on X, which means that you have a homomorphism from the group G to the group of bijections from X to X. Okay? So we'll call such a pair, or rather more the X, we'll call it a G set. So we'll say that X is a G set if it comes with an action of G. So given a G set, you can get a permutation representation of G. So what is it? It's the representation which I'll denote by rho subscript X, and the space is Kx. This is the vector space of functions from X to K. And the action is, the representation is given by rho xg. So now this needs to act on a function. This function needs to have a value at a point x. What should that be? And not hard to guess that it should be probably something like g dot x, but actually it needs to be g inverse x because of this left-right problem. So if you put g dot x, it won't be a representation. It will be a representation of the opposite group, whatever that means. Another way of thinking about this, which may do away with this problem of the inverse, is to think of this as a vector space with bases indexed by the points of x. So the function which is 1 at a point little x of capital X and 0 everywhere else. So you can write it like that: rho x g 1 subscript x is 1 g dot x. At least if x is finite, which is what we'll be assuming in this course, these are the same. Though sometimes it's interesting to look at infinite spaces x. So these are like the two different ways of looking at the group algebra, one as functions and one as a vector space with a certain basis. So the examples that we'll be looking at are the following. Let's denote by underscore n the set of the first n natural numbers. Then an ordered partition is a collection of subsets S1 union up to SL, which partitions n. So I say ordered, I just mean that keeping track of which is the first subset and which is the second subset and so on is important. So for example, 3 equals 1 union 2 union 3 is not the same as 3 equals 2 union 1. These are different ordered partitions. Okay. So if I let lambda I denote the cardinality of the subset Si, then the fact that these SIs partition n means that the sum of these things, lambda 1 up to lambda L, is equal to n. Okay, but again the order of these things does matter, lambda 1, lambda 2. For example, if I had 1, 2 disjoint union 3 and 3 disjoint union 1, 2, these would also be different ordered partitions, and their the lambdas associated to them would be different. So this we'll call the shape of. So lambda equals lambda 1, you can think of this as an L tuple, is called the shape of the partition. So in combinatorics, such an object that is just a sequence of a tuple of well, maybe positive, sometimes non-negative integers whose sum is n. Usually you would assume them to be positive, and I'll assume them to be positive for now, it doesn't really matter much, but is called a composition of n, and it's denoted like this. A partition of n is usually one when these lambdas are in some particular order. The reason is that in combinatorics, the partition problem, if you want to partition n, they don't distinguish between 1 plus 2 and 2 plus 1. They are the same partition of 3. But we are looking at ordered partitions, so we end up with compositions. But if lambda 1 is greater than or equal to lambda 2 and so on, which is greater than or equal to lambda L, then lambda is called a partition. You could equally well take the increasing order instead of the decreasing order, and the notation there is this. So these are two combinatorial notions that you should keep in mind. And I define x lambda to be the set of partitions of shape lambda. So what's the cardinality of x lambda? So it's a multinomial coefficient n factorial by because the question is like how many ways can you choose the objects that you put in these parts, and it should be a standard problem which you've seen before. Okay, so we've constructed a bunch of sets, and these are actually Sn sets. So this is a G space with G equal to Sn, right? So x lambda is an Sn space. How does Sn act? Well, if you have a permutation, it will just act on the elements on the set of natural numbers from 1 to n. Now those guys will be sitting inside partitions, and it will therefore move one ordered partition to another ordered partition. For example, here it's just the permutation with interchanges 1 and 2 will take this partition to this partition. So this, if you take lambda to be 1 plus 1 plus 1, the partition 1, the composition 1 plus 1 plus 1, then x 1 plus 1 plus 1 is just, this is as a S3 set is essentially the same as the set 1, 2, 3. There's no difference between this and the set 1, 2, 3. You can find a bijection which preserves the action of S3. Clear? So let's see, G dot, so now we have this partition S1 dot 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 SL is by definition GS1 GSL, where this just denotes the image under the permutation G of the subset. So with that, that's the example we are going to be looking at very closely soon. But let's go back to generalities. Our goal is to understand the intertwiners between permutation representations. And in order to do this, the language of integral kernels, which usually comes up in functional analysis, is intuitive and useful. So let's just develop that language. So there are no integrals here, everything will be a sum and set, then there's no continuity conditions on functions because we are looking at finite sets which have the discrete topology. So don't feel intimidated by headings such as this one. And so let K be a function, K-valued function on the set X cross Y. So it's clear what this means, right? K-valued functions on the set X cross Y. Then this is called this should be thought of as a kernel, and the integral operator with kernel K is defined as, so I'll just write it down. So what's happening here? F is evidently a function on the set Y, okay, and I'm using it to construct a function tkf, which is a function on the set X, with the help of this kernel little k. So this is just a definition for a linear operator from ky to kx. So it's called the integral operator with kernel K. So you can look at this thing, okay, so you have a function K and you can construct from it integral operator Tk. So this lives in K xy and this lives in Hom linear maps Hom K ky to kx. The first thing you'd notice is that this space has dimension cardinality of x times cardinality of y. This space also has dimension cardinality of x times cardinality of y. The second thing you may notice is that if k is non-zero, then tk is non-zero. You can just construct a function on which it is non-zero. You'll have to just think about that for a moment. It's easy. So k goes to tk is injective, and it's a linear map from a vector space of a certain dimension to another vector space of the same dimension. Therefore, it's an isomorphism of vector spaces. So given a linear map, you can also figure out what kernel it is an integral operator for. You should be able to do that in principle. Okay, so instead of looking at linear maps from ky to kx, we'll just be looking at the associated kernels. Now the question is, if we want to study, we know which linear maps we are interested in. We are interested in intertwiners. So then the question becomes, what are the kernels that the intertwiners come from? That's the question. For which k in kxy does t subscript k belong to Hom G ky kx. So this condition belonging to Hom G ky kx, remember what it means? It means that t sub k, when you compose it with, so it's going to kx, so I must take rho xg. This should be the same as t sub k composed with rho yg for all g in G. Or you can write it as rho xg circle tk circle rho yg inverse is equal to tk for all g in G. So this is the condition we want. So let's try to calculate this left hand side in terms of k and see if it's a kernel operator with respect to, it will be a kernel integral operator with respect to some other kernel, and for this to hold, that kernel should be the same as the kernel k, so we'll get hopefully a nice condition. So let's try to do that. So we need to calculate this thing. If you don't mind, I'll bring the inverse to the other side. Just the answer ends up being a little nice. So just by replacing g by g inverse in the previous equation, I can get this. So this is an operator on ky. So I'll feed it a function of y, and then it will do something and we'll get a function of x. So the question is, what is that function, right? So so this is rho xg inverse applied to this part. So that is tk circle rho yg f, and this needs to be evaluated at g dot x. Remember, here the g has an inverse, so g inverse becomes g dot x. Then we need to put in the tk bit, so that by definition is summation over y in y k of, now the argument is g dot x, so we put g dot x y and then rho y g f of y, right? So now we just sort out that bit. So that's G inverse dot y. Now we resort to the age-old trick of changing variables from y to G inverse y. If as y ranges over the set capital Y, G inverse y will also range over the set capital Y exactly once, because this is a group action. So if I'm going to replace G inverse y by y, I need to replace y by G dot y. And this is exactly the kind of answer we wanted. This is the new kernel. What has happened to the old kernel is that both the variables have got simultaneously shifted by the action of G, the same element of G. So what you want is that K should coincide with Kg dot x comma G dot y for every G in G. Okay? So let me just write that down. So the conclusion of this calculation is that Tk belongs to Hom, a G homomorphism Ky comma Kx if and only if K of G dot x comma G dot y equals K of x comma y for all x in x, y in y, and G in G. This lets us calculate the dimension of this space. When we looked at completely reducible modules, we saw that this dimension tells us a lot about the decomposition into simples. So the nice thing about this is it lets us calculate the dimension of the space. So dimension of this thing, Hom G Ky Kx, is the cardinality of the set. Well, I must take x cross y and go modulo the diagonal action of G. Okay, what it is G is acting on x cross y by G dot x comma y is by G dot x G dot y. So this is an action of G on x cross y, and this is the set of orbits. For this action. Let me give you a somewhat different sort of example of this. Suppose you take r cubed cross r cubed. Now r cubed itself acts on r cubed by translations. So you can ask yourself, if I look at the action of r cubed on r cubed cross r cubed, this kind of action, that is, so this dot will just become sum. Then what are the orbits? Okay, so the orbits are again vectors. The idea is somehow this thing that when we introduce vectors in school, we usually say a vector has a source and a destination. It's an arrow drawn from that. So think of this as a source and then as this as the destination. But then we move to add vectors, for example, we always move them so that their tail is at the origin. So that is, you move the tail to the origin means that you have an r cubed's worth of movement to do, and you can bring the tail to the origin and look where the head is, right? And so you say so this is the relative position between the tail of a vector and the head of the vector. So this is actually the relative position of pairs of points in r cubed, and it's just an element of r cubed itself if you wish, namely x comma, well, maybe we can call this t comma h, tail of a vector, and head comma vector goes to h minus t if you write down the coordinates of those things, and that's a vector itself. Right. So this is called relative position. And I'll borrow this terminology to apply to the most general case. So if you have two G sets x cross y, by the relative positions of a point x in x and a point y in y, I simply mean the G orbit of x comma y in x cross y mod G. Okay, so we'll say that 2 points have the same relative position if there exists an element of the group which simultaneously takes, 2 pairs of points have the same relative position if there exists an element of the group which takes each element of one pair to the corresponding element of the other pair. So x1 comma y1 and x2 comma y2 have the same relative position if there exists G in G such that G dot x1 is equal to x2 and G dot y1 is equal to y2. So one thing to note is that if x is equal to y, then you get the dimension of the endomorphisms, and it is x cross x mod G. And this set, if so long as x is not singleton, this will have at least 2 different relative positions, because you could have x is equal to y and x is not equal to y. If 2 points are equal, there's no way you can act on it by G simultaneously to make them unequal, and if they're unequal, there's no way you can make them equal. So that's like the crudest invariant of relative position, whether 2 points are equal or not. We'll look at finer invariants in different contexts, and we'll look for complete invariance. So that's the game. What's your question?
In general, cardinality of x cross mod G will just be cardinality of x times orbits.
So the cardinality of x cross y mod G cannot easily be calculated. I mean, I don't think there's any formula that relates it to the number of orbits in x and the number of orbits in y and the cardinality. Oh, for x equal to y. No, it won't be the cardinality of x into the number of orbits in x mod G. You will see some examples, and I think it's quite an interesting thing. It depends quite a bit on how this action is. An extreme case are what are called doubly transitive actions. So for doubly transitive actions, I don't know if you've heard the name or not. The definition in this parlance just means that this has cardinality 2. I told you it has cardinality at least 2. Well, it has cardinality exactly 2. Okay, I want to start with a toy example before we come back to this general x lambdas that I defined. This is a special case of the x lambda. what if you just take a partition with two parts rather than a partition with many parts? So a partition with two parts is just determined by one of the parts because the other part is a complement. So essentially we're looking at partitions of two parts, we're looking at subsets. And the shape is determined by the cardinality of the subset. Okay, so x k comma n minus k is the set of subsets of 1 to n of cardinality k. So I'll denote it by x subscript k for now. So this is subsets of n such that cardinality of S is equal to k. And you know how many elements there are in this, n choose k elements. So let's just ask ourselves, if I gave you two pairs, one subset of cardinality k and say two subsets of cardinality k and two subsets of cardinality L, and I ask you the first pair one subset of cardinality k and one subset of cardinality L, and the second pair subset of cardinality k and subset of, can I simultaneously sort of move one to the other? And if you think about it, suppose you can, then the cardinality to the intersection is preserved. Okay, that's the only thing that you need to worry about. If the cardinality of the intersection is preserved, then you can move one to the other. So the point is that S comma T maps to cardinality of S intersect T is a bijection, induces a bijection from, okay, we'll have to figure out what the range is, but so it's just a natural number, we know that, and certainly it must be between 0 and the minimum of k and L, but it can't always be 0. It turns out to lie between min kl is the largest value it can take. The smallest value it can take is so I'll write it as an interval, but I mean only the integer points in this interval. Max of 0 comma k plus L minus n to min kl. The point is that if k plus L is larger than n, then the intersection cannot be 0. It has to be at least k plus L minus n. Okay, but if k plus L minus n is less than 0, the intersection still cannot be negative, it can be 0 only. So you must take the larger of 0 and k plus L minus n. That's the smallest possible intersection. And the largest possible, of course, is when one subset is contained in the other, in which case you get minimum of k comma L. So you get the cardinality of this as this minus this plus 1. Right? That's the cardinality of an interval of integers. Now we'll use this to determine how kxk decomposes. Let's assume also that the characteristic of k is large enough so that this is completely reducible. So for sufficiently large, and assume that capital K is algebraically closed, though I'm not sure, I don't think we need that. Okay, so first observation is that xk is isomorphic to xn minus k as a Sn set. That means there's a bijection from here to here which preserves the action of the symmetric group. What is this bijection? just take a subset to its complement. So by this I mean that there's a bijection phi such that phi g dot x is equal to g dot phi x. That's what I mean by bijection of G sets. This is the condition. This means that kxk is isomorphic to kxn minus k. You just given a function on this, you can get a function on this by using this bijection, and the actions will correspond, so you'll get an isomorphic intertwiner. So these are isomorphic. So if we are looking at n equals 10, we only need to go up to 5, and then 6, 7, 8, 9, 10 will be the same as 5, 4, 3, 2, 1. So we can assume that k is less than or equal to n by 2, and thank God, because if k is less than equal to n by 2 and L is also less than equal to n by 2, then this nastiness doesn't appear. So then you're just going from 0 to the minimum of KL, right? So for KL less than or equal to n by 2, let me write down a table showing the dimension of the homomorphisms So this will just be minimum of k comma L plus 1. So I'll just draw it as a table. So here's k along the columns and L along the rows, and we start with 0 in fact, right? You can take, there's just one set of cardinality 0, but we want to keep that also. So that's a singleton thing. Then 1, 2, 3, and so on, and the answer here is minimum of 0, 0 plus 1, minimum of 0, 1 plus 1. Okay, and this is going to be symmetric. It's symmetric in K and L. So okay, 1 and 1, minimum is 1, so that's plus 1, you get 2, and you'll get 2 here, 2, 2, then 2 and 2, that's 2, so you get 3, but minimum of 2 and 3 is also 2, so you get 3, and so on. So it's this kind of a creature. You get the idea. So are you done with this board? It's easier if I just go back this way. Okay, so what can we say from this picture? Let's assume that all these kxi's are completely reducible, otherwise we are not really in a position to figure out the simples. So what this says right off is that kx0 has a one-dimensional space of endomorphisms, and now you all know by now what this means. It means that this is simple. So kx0 is simple. We are going to build a collection of simple representations. So this will be the first guy in my collection. I'll call it V0. X0 is the set of subsets of n of cardinality 0. So it's a singleton set. Yeah. So kx0 is a one-dimensional space, and the action is of course trivial. So it's not hard to guess what the representation is. It's what's called a trivial representation. But let's just, I mean, we don't even need to make such observations. We know just numerically that this is 1. And you'll see why I'm using this perverse way of seeing that it's simple rather than, of course, we know. Because at the next stage I'll need to do it. Now what does this one tell me? So this is the dimension of the homomorphisms from the simple kx0 to kx1. So what it's telling me is that v0, that simple kx0, occurs only once in kx1. This one tells me that v0 occurs once in kx2. So on. So what I see is that v0 occurs once in kxi for all I greater than or equal to 0. So I can write kxi to be v0 direct sum some other representation kx, oh this I is inside I, and I'll put a subscript 0 here to indicate that I have removed the v0. And in this, if you look at the decomposition to simples, there'll be no v0. Okay, so now let's calculate dimension of Hom kxi. So this is for I goes from, well, it's true for I goes from 0, 1, 2, but well, let's just put 1 because for I equals 0 this part is trivial. So we'll just look at I goes from 1, 2 and so on. And the question is, what is this? I guess I was using K and L. So I just need to take the whole thing and remove the contribution of V0. And V0 occurs once here and occurs once here. So when you take the formula for the homomorphisms from here to here, it's summation mi-ni, where mi-ni are the multiplicities in the first one and the second one. So m1 and m0 and n0 are both 1. So the contribution is just 1. So I must subtract 1. So I must take this matrix here and subtract 1 from everything to get my next table, which is dimension of Hom kx little k 0 kx little l 0. So now the table starts at 1 and I must subtract 1 from those entries. So this process has some self-similarity built into it. Now, just as before, I can infer that kx10 is simple. Because its endomorphism algebra is one-dimensional. So kx1 itself is v0 direct sum v1. Kx1 is v0 direct sum kx10. So kx1 is v0. And now I can look at I can look at each kxi0, and what this table tells me is that v1 occurs exactly once in it. So this is v1 direct sum k, some new representation I'll call kx1, and kxi is v0 direct sum v1 direct sum kx1 for I let's say greater than or equal to 2. When I is 1, then there's nothing here, it's just v0 direct sum v1. And now this process you continue and you keep shaving off pieces from the kxi's, and the theorem you get is the following. There exist simple representations, maybe I should say pairwise non-isomorphic, v0 v1, and how far does this go? It goes up to floor of n over 2 of Sn such that kxi is the sum of v0 up to vi. So this is how you can just combinatorially, by studying relative positions, resolve an entire family of permutation representations. So it just seems a bit lucky that it worked here. The interesting point is that this will work for all the partition. I described these spaces x lambda. It will work for all those representations, all those permutation representations. But it'll take some convincing to convince you that it works. So we'll get there slowly. But another point I want to emphasize, okay, so what's the dimension of vi? Well, we know the dimension of this is n choose I, and so if you go up to I minus 1, that's n choose I minus 1, because that's just kxi minus 1, so this is n choose I minus n choose I minus 1. So here's another proof of the unimodality of binomial coefficients. Right. So for n equals 3, what do you get? You get that dimension of v0. Well, dimension of v0 is always going to be 1. You know it's a trivial representation. Dimension of v1 is going to be 3 minus 1, so that's 2. So you've constructed two irreducible representations of S3, one of dimension 1 and one of dimension 2. We can even use this to calculate the characters of these representations, because it's not so hard to figure out the characters of these representations, and then inductively you can subtract the, if you want the character of vi, you take the character of kxi and subtract the character of kxi minus 1. You remember how to do this? It's just the number of fixed points for the action of Sn on xi. So let's just do a simple example for n equals 3. So when you have to calculate the character of a representation, you just need to calculate it for one element in each conjugacy class. And I hope you all know that the conjugacy classes in the symmetric group are determined by the cycle decompositions, and those are just partitions of n. Okay, so the cycle decomposition 1, 2, 3 is isomorphic, is a conjugate to the cycle decomposition, say 2, 1, 3. It's not, okay, you can put these in any order you like, they commute. So you really want to, you can take the lambdas, the parts in, you can rearrange the order of the parts of the partition. So it's not compositions, but actually partitions. So what are the partitions of 3? There are 3 of them. So for 3, there's the identity element, then there's the transposition which just interchanges 1 and 2, and then there's the cyclical thing which takes 1 to 2, 2 to 3 and 3 back to 1. These represent all the conjugacy classes. This corresponds to the partition 3, this corresponds to the partition 2 comma 1. So this is element, this is partition, and this corresponds to the partition 1 comma 1 comma 1. And now let's write down the character of row x, let's say 2 G on kx2, not 2, 1, we have only, okay. And well, this we know is just the dimension, so that's 3. Okay, what is kx1? So kx1 is the set of all subsets of cardinality 1. So we can really just think of it as the set 1, 2, 3 itself, and S3 is acting on it. Okay, so how many fixed points does this interchange of 1, 2 have? It only fixes the point 3. So here I should put 1. The identity fixes all the points, that's why I got 3 here. And this guy fixes no points because it just slides each point along in this ring with 3 elements. Okay, so this is 0. But suppose I wanted to calculate the trace of this representation V1. Let me just create a little space here. Then I would have to subtract from it V0. So I have to subtract 1 from each of these. So I get 2, 0, minus 1. So that two-dimensional representation has this character. In principle, you can do this for any n and any I. So not only have we constructed a huge family of representations, we've also obtained an algorithm for writing down their characters. And you can check that this has the property that an irreducible character should have. That is Schur's orthogonality, actually the norm more like, rather than orthogonality. Okay. Okay, let's see what we can say about general compositions now that we warmed up. So suppose we have lambda and mu, both are compositions of n. So just to fix notation, whenever I write lambda, I'll mean lambda 1 comma up to lambda L, and whenever I write mu, I'll mean mu 1 up to mu m. And what we know is that these lambdas and these mu's, they add up to n. So lambda 1 plus dot 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 plus lambda L is n, mu 1 plus dot 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 plus mu m is n. And let's take S equals S1 disjoint union SL, this partition of shape lambda, an ordered partition of shape lambda, and S prime so we want to somehow find invariants of the relative position of S and S prime, so that given two such pairs S and S prime and say another one T and T prime, we can tell whether the relative positions are the same or different. In other words, whether there's an element of the symmetric group which takes S to T and S prime to T prime. So we want to see how we can measure this. So one, taking a look at the previous example where we just looked at two subsets, we noticed that all we need to do is to keep track of the cardinality of the intersection. So let's do that. Let's keep track of the cardinality of the intersections of things here with things here. So let's define R subscript ij to be Si intersect Sj prime. And let's arrange them in the form of a matrix. R11 up to R1m, and here RL1, RLm. So this is an L times L by M matrix. And suppose I add up the entries in the first row, what do I get? Well, I'll be looking at, so I'm varying the second coordinate, so I'll be looking at S1 intersect S prime 1 cardinality plus S1 intersect S prime 2's cardinality plus so on. But that's just a partition of S1 itself. So these should add up to lambda 1. And similarly, each row should add up to lambda I, and okay, so this should add up to lambda L. The ith row should have some lambda I. What about the columns? It goes the other way around. So now I'm fixing j and I'm letting I vary. So I get the mu's. So here I get mu1 up to mu m. At the jth stage I'll get mu j. So so these numbers, now we have so many of them, we've been able to organize them nicely. We get a matrix whose entries are all non-negative integers, whose row sums are lambda and column sums are mu. So okay, now I want to claim that this is actually a bijection. That is, if you simultaneously permute S and S prime by some permutation, then these cardinalities will not change. So this R, you take S comma S prime to, let's call this matrix R S comma S prime. This induces a map from x lambda cross x mu mod Sn to m lambda mu, where m lambda mu denotes the set of all non-negative integer matrices, that is matrices with non-negative integer entries whose row sums are lambdas and column sums are mu's. And I want to claim that this is a bijection. So I'll call this R. Can I erase this? Or shall I just go that side? It's okay. So I claim that R is a bijection. That would mean that if I can count this number, then I can count the dimension of the space of intertwiners between two of these partition representations. So we need to show injectivity and surjectivity. For injectivity, suppose all the intersections have the same cardinality. Okay? So then what you do is you prepare a partition into L times M pieces. So what is the point? So suppose R of S prime is equal to R of T prime. Then we need to construct a permutation which takes S to T and S prime to T prime. Now the subsets Sk intersect S prime L have the same cardinality as the subsets Tk intersect T prime L. These have the same cardinalities. That's what it means for the R's to be the same. So they are in bijective correspondence. So I can just define a function from n to n which takes each of these subsets to each of these subsets. They also partition n because Sk by itself partitions n, and then this you can think of as L varies as giving a partition of Sk. So overall this gives a partition of n. Maybe some parts are 0, but it doesn't matter for the purpose of our argument. So you just find a permutation which takes each of these paths to each of these paths, and that will give you a permutation which takes S to T and S prime to T prime. Yeah, I guess that's the only point. And now let's see how to show surjectivity. So given a matrix whose row sums are lambda and column sums are mu, how do I construct a pair of ordered partitions with those cardinalities of intersections? So what I do is I prepare those sets of intersection first. So what I do is I'll just define a set. I'll write a partition of n of this form. I'll just partition n into k times l pieces where the cardinality of the kth piece is rkl. Right? And then I'll take sk to be the summation, the union over L of AKL, and S prime L to be the union over K of AKL. And then the intersection of SK and SL prime will be precisely AKL because of the way these sets are pairwise disjoint. So the only one that's common in this intersection is the KLth piece. Great. So we've got our first sort of nice combinatorial theorem. Is equal to the number of, I guess I'll just use m lambda mu, the number of matrices, L by M matrices with non-negative integer entries such that the ith row adds up to lambda I for each I and the jth column adds up to mu j for each j. So this is a nice counting problem. You want to count such matrices. Let's just try it out for the simplest case. Well, okay, before we do that, I just want to do a cute trick. So, so suppose I take the parts of lambda and permute them. Will this number change? So suppose instead of 2, 1, I write 1, 2. It will not change because I could take a matrix whose first row adds up to 2 and second row adds up to 1 and interchange its rows, and then I get a matrix whose first row adds up to 1 and second row adds up to 2. So these numbers are invariant under reordering of the parts of lambda and mu. So what we get is that, so let me just use this shorthand, lambda mu, yeah, so no, let's just do it like this. If lambda is a reordering, let's say if lambda prime is a reordering of lambda, then I could look at dim hom kx lambda kx lambda prime, and I could equate it with dim Hom. I can change the order of this. I can replace it by lambda prime. Or I could change this and get so do you know what this means? In the completely reducible case, this means, okay, so suppose you write down the multiplicities of the simples as vectors, then this is the dot product of the two vectors corresponding to lambda and lambda prime. That's saying that's the same as the norm of the vector corresponding to lambda prime, and that's the same as the norm of the vector corresponding to lambda. So you have two vectors whose dot product is the same as each of their norms, and that means that they are equal. So that means that kx lambda prime and kx lambda are isomorphic in the completely reducible case. So in the completely reducible case, this means that kx lambda is isomorphic to kx lambda prime. So what we can do is we can reorder the parts of lambda and put them in decreasing order, or what one should strictly call non-increasing order. And so it's enough to consider the case where lambda is a partition. Partitions of n. Okay, so with that reduction in what we have to calculate, let's do a simple example. So I'll look at S3, kx lambda, kx mu. So there are only three partitions. Three, 2 plus 1, 1 plus 1 plus 1, 3, so this 3 means that let's say lambda is the row sums, right? So 3 means that there's only one row and its sum should be 3, right? And there's only one column and its sum should be 3. So it's just a 1 by 1 matrix with entry 3. That's the only possibility. Okay, what does this mean? So this means that there are two rows. The first row should add to 1, the second row should add to, the first row should add to 2, the second row should add to 1, and the total should be 3. This is a hugely overdetermined thing. So this has to be 2 and this has to be 1. In general, if you have, okay, so there's only one more case left, but suppose you had more things. These row sums tell you exactly what to put in the one and only column of the matrix, and it's all determined. So, and this is going to be symmetric because you can just transpose the matrix and get the other thing. Okay, and now let's see 2 plus 1 and 2 plus 1. So now we're going to look for 2 by 2 matrices. Now there are two possibilities. So can I put a 0 here? Well, if I put a 0 here, the largest I can put here is a 1 because this column has to add up to 1. So then I can't get 2, so I have to put at least 1 here. Okay. Suppose I put 1 here, this needs to add up to 2, so I have to put 2 there, 1 there, 1 here, and then the 0. Okay, and then suppose I put 2 here, then I have to put 0 here, and 1 here, so I get 2. Then I need to do a 3 by 2 matrix calculation. So I want 1, 1, 1 here, I want 2 here and 1 here, or maybe it's the other way around. Anyway, so what I need to do is I need to put a 1 either here or here in each column. But I need to choose 2 columns where I put the 1 upstairs and 1 column where I put it 1. So I get 3 choose 1. So I get 3. And here I need to get 3 by 3 matrices whose rows add up to 1 and columns add up to 1 and all entries are non-negative, which just means that each row has exactly 1 1 and all other elements are 0. Those are just the permutation matrices, so there's 6 of them. Okay, so we see that right away we can start working the way we did last time. We've got a 1 over here, so we know that somebody is simple. So we'll call kx3 is simple, so we'll call v3 kx3. And then we'll write kx lambda. So also we know that v3 occurs once in all the other kx lambdas. So each kx lambda can be written as v3 direct sum kx lambda, and we should give it some new name, so I'll put a 3 over here. Now you ask, what is the dimension of the endomorphisms of these things? Dimension of homomorphism of these things, and it's the same story. Dimension of homomorphism of kx lambda 3 kx mu 3 S3 is the same as the old dimension minus the contribution of v3, which is 1 here times 1 here. Okay, how many ever times it occurred here times how many ever times it occurred there. So 1 times 1. So we can draw a new table now. So v3 is kx3. We don't worry about kx3 anymore. We write 2 plus 1 and 1 plus 1 plus 1. 2 plus 1 and 1 plus 1 plus 1. And hey, 2 minus 1 is 1. Okay, here something new happens. Now we've got a 2 here, we've got a 2 here, and we got a 5 here. So now the story has changed a little. We still know that this kx2 comma 1 subscript 3 is simple. But what's different is it occurs twice in kx111 subscript 3. So now we'll define kx111 subscript 21 as kx111. Well, actually we put the sum here. This guy occurred twice. So we remove that part, and what's left we call kx11121. Okay, in the completely reducible case, you can almost subtract representations by subtracting the multiplicities. So this is what we get. And now the question is, what is the endomorphism of this guy? Sorry, here I should put a 3. So that is 5 minus what? So this guy contributed a 2 to this representation, and that gets multiplied by another 2 because I'm taking the harm from this to this, right? So minus 4, and that's amazing, it's 1. So what we get is that kx11121 is simple. I'll call it V111. And what have we got about the representations? The permutation representations, what we've got is that kx3, well, that was already simple, we called it V3. kx21 was V3 direct sum, something new which we called V21, and kx111 is V3 direct sum V21 which occurs twice. Now let's just focus on this kx111. So this is the set of partitions of the set 1, 2, 3 into 3 parts, but ordered partitions, right? So I claim that, so how many of these are there? So they are just 1, 2, 3, but I can take any permutation of the set 1, 2, 3 and put those. So sigma 1, sigma 2, sigma 3. So sigma goes to sigma 1 disjoint union sigma 2 disjoint union sigma 3 gives a bijection between Sn and x11111. And this is in fact a bijection of Sn sets. It preserves the Sn action. So this is nothing but the regular representation of S3. So we've actually calculated the decomposition of the regular representation of S3. And in the regular representation, we know that each simple occurs as many times as its dimension. So without even sitting down and calculating things, we know that this is 2-dimensional and these are 1-dimensional. And from this, you can also write down the character table of S3. So this calculation seems a bit miraculous, that somehow, you know, we had that 6 which looked really terrible, and then it became 5, and then somehow 4, and then we were only left with 1. You try this for S4, you try this for S5, it's a magic trick. You always end up with being able to resolve all the irreducible representations of Sn. So somehow this procedure will always work. I have already given you an algorithm for classifying the irreducible representations of Sn. I have not given you a proof that this algorithm will work, but this algorithm for each n will give you a proof for that n. So you should try it for 4, for example, n equals 4. The reason it works is something called the RSK correspondence. So we'll look at that next.